Hello, welcome. Today's topic is experimental designs for fitting response surfaces. Experimental designs for fitting response surfaces. So, the contents of today's presentation are features for selecting response surface design, design for fitting first order model, designs for fitting second order model. Under this we will discuss central composite design and box Venken design, and there are some references. Primary source of lecture material is chapter 11 of the book entitled Design Analysis of Experiments by Montgomery, which is published by Wiley 8th edition. So, let us first look back little bit. So, when we talk about experimental designs, in the first few classes I have explained the names, and then thereafter what happened, we have elaborated all those designs and the experimental data based on those designs need to be analyzed, and the analysis schemes were also given to you. For example, we have started with one factor randomized design, complete randomized design, then complete randomized design with blocking, then we have gone for two factor design, three factor multifactor design, then special class 2 to the power k factorial design, then 2 to the power k minus p fractional factorial design, and so many things. So, thereafter we have started the in last lecture we have started with response surface methodology, response surface methodology RSM, response surface methodology, and I have explained the first order model with a design called factorial design with central point, factorial design with center point. So, in today's lecture we will discuss those popular designs, experimental designs which are used to fit response surfaces. So, that is why I have written that design for fitting response surfaces or experimental design for response surface methodology. We will start with the first order model, and then we will go for second order model. What are the different kinds of design are needed? So, if you look back the first order model, first order response surface, there we have used factorial design with center point. These are the factorial points and this is center point, and with coded term x 1 x 2, obviously with reference to two factors. So, there will be more factors, then it will be basically factorial design with center points. So, at the factorial points usually one run experiment is conducted, but at the center point several experimental runs are conducted, and it is a very important point because at this point the data will give us to estimate the MSE, mean square error, which is basically also a estimate of sigma square. Okay. So, we will go by this manner, that first we will see that what are the features that is important for selecting response surface design. So, the design should provide a reasonable distribution of data points throughout the region of interest. So, the operating region, operating zone of interest or region of interest for the behavior of y which is response variable and which is known to the process engineer or the experts. So, your design should give valuable information on the behavior of the response at any point on the design surface or design space. So, design allows model adequacy including lack of fit to be investigated. So, that means the data what you collect that must represent the population and must be sufficient in size, so that the adequacy of the model used for analyzing the data will be found out, and also at the same time the lack of fit. I think if you can recall the regression lectures where we have described lack of fit. So, lack of fit also to be estimated. Then the design should be such that it allows experiments to be performed in blocks, very important, because you know randomization, blocking and replications are the three basic principles, and designs any experiments, they are dependent on useful resources including raw materials. So, you require to do either intentionally blocking or you are forced to do blocking, but blocking is an important one and your design should allow you to do this. Design of higher order to be built up sequentially, that is what we have discussed in 2 to the power k factorial 2 to the power k minus p fractional factorial design. So, that means you design should be sequential, so that the higher the order of interactions, if you require to estimate those orders of interactions, it can be estimated. The design provides an internal estimate of error. So, this is that a part of this is basically the error part. So, estimation error is very important. It is basically that between levels, within levels, all kinds of errors must be estimated. Provides precise estimate of the model coefficients. So, what does it mean? The beta value, regression coefficient or the effect in ANOVA you use, this should be estimated in such a manner that the variance of those estimates should be the minimum. So, that means your design should allow you to avail the minimum variance estimates. Design should provide a good profile of the prediction variance throughout the experimental region. So, when you using the analysis of the model you employ for analyzing the experimental data, that model ultimately will give you the response surface kind of thing, and you want to predict or you will get regression model, you want to predict the output or response value. Now, the predicted variable value that must be within having the variance part, that also should be at the minimum level. So, what do you want, that the data what you get out of the designed experiments, it will allow you to have or develop a good profile of the prediction variance, and obviously throughout the experimental region or design space. Design provides reasonable robustness against outliers or missing values. This is another important feature, because many a times what happened, you may encounter outliers or some assailable regions which causes your experimental runs to be skewed to certain direction, or you may miss some values to record properly. Under such situation, the missing data handling and outlier removal, all those things is required, and at the same time even if all those things are done, the outcome of this will be so robust that you can use the experimental data for the objectives for which the design was done. So, design does not require a large number of runs. Large number of runs means costly. So, it should be the minimum possible runs, obviously representative one. So, that sample size determination we have, I think two lectures on sample size determination. So, you have seen that how the sample size is determined. So, what you want, your sample size should be representative, but at the same time it should not be so high that it will there will be cost overrun. Design does not require too many labels of the independent variables. Suppose you have five factors, and if each factor is having 5 labels each, so there will be 5 into 5, 25 treatment combinations. So, this is probably a little exhaustive. We do not want such high level of labels or so many treatment combinations. With minimum labels, what maximum information that can be achieved. So, that should be we got from the we must get from the design you employ. Design ensures simplicity of calculation of the model parameters. For example, you will be able to use ANOVA, because ANOVA is a very simple one, easy to understand, very powerful, effective. So, it should be your data should be such that it will help you doing ANOVA. For example, sometimes if you consider continuous factors along with categorical factor at different levels. So, what will happen, you may require analysis of covariance or some other kind of model, but it is always better if you can make it simple. So, that maybe the simple ANOVA will work there. So, please keep in mind all those features while choosing a design. Now, let us discuss first order model, and this model you have seen earlier, and here what happened, we say that we want to adopt orthogonal design. Now, I have given you X matrix, which is basically design matrix, and we have shown you earlier that if you with coded variable, that if you take the dot product of two of column of the design matrix, including the factors of interest, you will find out that dot product is 0, which means that orthogonality is obtained. So, now you can find out by computing the X transpose X. If your design matrix is X, then X transpose X, when you compute, if the design is orthogonal, then what will happen, the off diagonal elements of X transpose X become 0. So, for orthogonality X transpose X, or we are defining like this, X transpose X matrix contain 0 off diagonal elements, valued off diagonal elements. So, for first order model, 2 to the power k factorial or 2 to the power k minus p fractional factorial design is sufficient. The reason is what you require in first order model, you require that the main effect should not be aliased with other main effects, because your model is first order, only main effects you have considered. So, 2 to the power k factorial or 2 to the power k minus p fractional factorial will work there, like the factorial design with center points. This is a very good design. That means, this one is 2 to the power 2 design with center point. And there is no replication at the center point at the factorial points. And another design that is also used in first order is known as simplex. We will not discuss this, but the simplex by definition is a regularly sided figure with k plus 1 vertices in k dimensions. So, we will come to the second order response surface designs. I have explained the first order response surface in last 2 class. So, I told you that when you achieve the using first order response surface model, you achieve the point of optimum. So, if you start from here and you ultimately your direction will be given by the first order model, and then what happen, your that is experimental runs here, you start running. So, the experiment and you get the y result, and ultimately this is the zone where you require second order model, because first order will not be fit here, and to understand that whether optimality is reached or not. So, that means in the second order we require second order model here, and second order model ultimately has more number of parameters, and such design like this to the power 2 k with center point, or to the power k factorial to the power k minus p factorial will not be able to provide sufficient data, so that the parameters of a second order model can be estimated, all the parameters second order model can be estimated. So, you require more information, you require special kind of design, and those design are discussed here. Now, see, we are saying that central composite design and box Benken design. This one is central composite design. What is central composite design? So, central composite design has three types of three types of points, I can say. What is this? One is factorial points, which are the corner of this rectangle, axial point, and the center point and axial points. Please understand this. With reference to the power 2 design, k equal to 2, with reference to the power 2 case, here you have 4 factorial points, 1 center point and 4 axial points, and the distance from center point to any of the axial point is alpha. So, you require to find out the value of alpha, that is important. This axial point is also known as star point. If it is 3 factor case, then you will be getting the cube, and there will be 8 factorial points, 1 center points, and obviously how many faces are there? 1, 2, 3, 4, 5, 6. So, accordingly the axial points will also be chosen. Axial point will be chosen along the 3 dimensions both side, and it will be alpha distance apart from the center point plus minus alpha distance apart from the center along. There are, when there are 2 factors, 2 axes. So, 2 into 2 4 axial points, 3 factor 3 axis, 3 into 2 6 axial points. Now, issue is that what will be the alpha? Alpha is chosen and depending on the value of alpha, the design central composite design also classified as spherical central composite design, when alpha equal to k to the power half, rotatable central composite design when alpha equal to nf to the power 1 by 4, where nf is basically the number of factorial runs, and face centered CCD when alpha equal to 1. That means the axial points are all on the middle of the side of the polygon. Okay. So, CCD have 3 kinds of that points, where the other way I can say settings, where the experiments need to be conducted. One is factorial points, another one is central point, another one is axial and star points. Depending on the k value of number of factors, the number of runs as will be chosen. Depending on the alpha value chosen, it can be spherical CCD, it can be rotatable CCD, it can be face center CCD. Now, let us understand what is the concept of rotatability. Rotatability, an experimental design is said to be rotatable if the variance of the predicted response at any point is a function of the distance from the center point. For example, you consider this figure. Here temperature and time and is plotted along x and y, and along z the response is variance part is part is plotted. Now, what happened? What is the center point? What is the center point here? You have already seen. So, now you take any distance from the center point, and then you measure what will happen. You measure the variability of the predicted response at a point, at all those points which are equidistant from the center, then the variance will be same. That is the rotatable one. If from through the contour plot, you can understand that if suppose this is the center point and then this is what is the distance. So, you see that the what happened, the variance part along this contour line, these are basically same. Okay. So, they are same distance apart. This is one. Now, how do you compute the variance? Variance of predicted response at any point is sigma square x transpose x inverse x. This is what we have discussed earlier, and in regression time also we have discussed this. This variance is the same at all points that are at the same distance from the design center. Okay. So, now this is one example of CCD. So, you see that this is a 2 to the power 2 factorial points. So, 4 factorial points, that is a minus 1 minus 1 minus 1 plus 1 like this, and then there are center point is 85 and 175, 5 runs at center points, and then there are 4 axial points runs are there. So, if you conduct experiments based on all those experimental settings, either through that means if you can very easily understand from this coded variable, and this can be this must come from the natural variable, and you conduct the experiments accordingly, and you will get the y data, that is the response data, and this response data can be used actually this design along with response data will be used to fit the second order response surface. Okay. Now, here is a comparison. For example, whether should we go for 3 to the power k design or CCD. 3 to the power k means every factor at 3 levels. For example, what you are doing here, if you see that go along any dimension, suppose x1, what are the design points? 1, 2, 3, here also 1, 2, 3. In addition, here these two are there, this point is there. So, what we are saying that instead of this, if we say x1 at 3 levels and x2 at 3 levels, then because then we will get this design 3 to the power k design. Now, here what we are comparing that number of experimental runs when k equal to 2 to k equal to 5. If you go for CCD and if you go for 3 to the power k design, what is the difference? So, from number of runs point of view, if your number of factor is 2, then CCD requires 13 runs if your central point run is 5 in number, whereas 3 to the power k design requires 9 runs. But when you go for k equal to 3, 4, 5, immediately you see that the reverse picture, the number of runs required for CCD is much less than the number of runs required for 3 to the power k design. So, what we can say here from this, that as in order to fit the second order surface, CCD is an efficient and better one compared to this, provided the purpose for which the model is built is served, means you will get the enough information on the entire design space, and that is what is possible also using CCD. Now, another one important one is if you choose alpha equal to that 2 to the power half, then actually k to the power half, then with spherical design when k equal to 2 and k equal to 3, k equal to 4, the values are given, and if you say no we want the rotatable one means the variance at the predicted response at a distance from equidistance from center point will be equal. So, then if you compare this, what you are getting the alpha value, they are more or less similar. So, that means a rotatable design and a spherical design is a rotatable one and other rotatable one is spherical one, that sense with little marginal difference, it is almost equal, at least up to k equal to 5, that is what is given in this slide. So, fine, but what will happen if you require 3 level factorial design, 3 level factorial design. We have seen that if I go for 3 level factorial design instead of 2 level factorial design, and if I employ CCD and if the purpose is served, then what happened, we are preferring CCD for 2 level factorial design, but the situation is such that 2 level will not give you the required information, you require to go 3 level. So, under such situation what happened, your number of experiments will be large. So, how can you make it efficient from number of experiment point of view, and also at the same time you will get the required information, so that the purpose for which the data is collected will be served. So, one such design is given, one such approach is given by Box-Benken, and the designs adopted based on Box-Benken approach are known as Box-Benken design or BBD. The historical perspective of Box-Benken design is that Box-Benken designs are 3 level factorial design developed in 1960. Actually, these are formed by combining 2 to the power k factorials with incomplete block designs. So, that means you do 2 to the power k factorial design and then do another one, and finally, you combine that means in the sequence you can combine them. In a spherical design with all points lying on the sphere, it is a spherical design, and with all points lying on the sphere of radius 2 to the power half, does not contain any points at the vertices of the cube. So, know that vertices means we have seen in factorial experiment that in the cube the vertices these are the settings. So, but here what happened, does not contain any point on the vertices of the cube. So, this is not correct. So, then used to estimate second degree polynomial, obviously the second order response surface can be fit. No general rules for defining samples. So, tables are provided by the authors, that means the sample size and other things. So, it is a group of tables are provided by Box and Benken as the starting point. So, we can use those tables for experiments. Here one example for Box-Benken. So, we have 3 labels. So, x1, x2, x3, 3 variables. So, you see that ultimately this is what is the design. How you are doing it? You are considering, you see that there are 3 factors x1, x2 and x3, and you are basically at a time you are basically choosing the 2 to the power 2 factorial design for a run. For example, run 1 x1 at -1, x2 at -1 and x3 at 0. So, this is run 1. Run 2, So, that means first what you do, you find out to the power 2 factorial design for the first two variables, and the say third one you keep and put it 0, means it is at the center point. So, then you go for the second two variables and the third one will be at 0 level, and in this manner you go. So, if you proceed in this manner, what happened, there are three variables x 1, x 2, x 3, and first you consider x 1 and x 2, and you know that to the power 2 means 4 factorial runs. So, that means you have 4 runs for first combination x 1 and x 2, where x 3 will be 0. Second combination x 1 and x 3, x 2 will be 0, that is another 4, and third combination x 2, x 3, when x 1 is at 0 level, that is another combination, another 4. So, altogether that means you require 12 experiments to be conducted in this manner. In addition, what happened? You require experiment at the center point. Okay. So, that means -1 low and +1 high, but 0 is basically the middle value, the central point value. So, first 12, in this case for k equal to 3, first 12 experiments are done by considering to the power 2 factorial design for 3 combinations x 1 x 2, x 1 x 3 and x 2 x 3, and the last 3 experiments are will be conducted using the center point. So, what I mean to say here, you require here 15 experimental runs. Suppose if you say no, I do not conduct 3 experimental runs at the center point, only one you want to conduct, then at least 13 you require. But at the it is customary that at the central point you consider more number of runs, because this will give you this will allow you to estimate error independently, and your tests, other things will become more robust. And at the same time, what happen, the center point is the point which is the most familiar to the operators. So, using this analogy, what happened, the 3 factor tables, 4 factor tables, 5 factor tables are provided by the author. Here you see that 3 factor tables, what I have explained, plus minus 1, this is the first one is the combination for to the power 2 factorial design for x 1, x 2 and x 3 will be at 0, that means 4 observations runs required. Similarly, second one, third one, 4 into 3 12 plus 1 13 minimum, but at this level we require more, maybe 3 to 5. Then in case of 4 factors, what happened, you see what you have done, first any 2 to the power 2, here to the power 2, then here to the power 2. So, that means 2 to the power 2 combinations you make. So, how many out of 4 factors you require 2 factors at the factorial case. So, that means you have how many such combination, 4C2 combination, that means factorial 4 by factorial 2 and factorial 2. So, that means 4 into 3 by 2, 6 such combinations will be there. Okay. So, here one, this will give you 4, this will give you 4, 4, 8, 8, 8, 24, and then again center points are there. So, if you go for 5 factors, accordingly you see that 2 combination, to the power 2 combination you use and find out all the design settings, means the point, the combination for the different factors where you will conduct the experiment. Okay. So, here we are giving you some comparative study in terms of number of runs. When number of factor, when it varies, that Box-Benken versus central composite, how the number of runs varies. So, Box-Benken started from 3 or more factors. So, if it is 3, Box-Benken requires 15 runs, central composite design requires 20, including 6 center points run. 20. Okay. Then when number of factors is 4, Box-Benken 27, central composite 30, number of factors is 5, this is 46, then 33 fractional factorial or 52 runs for full factorial, and 54, then here central composite also 54 with fractional factorial, but 91 with full factorial. So, what is happening here then? So, if the number of factors when it is increases, so if you go for 3 to the power, Box-Benken is 3 level design and central composite design is 2 to the power k level design, and with center and axial points, here the number of runs are required more when you go for full factorials, but Box-Benken design matches with the fractional part, or it is giving the efficient results. So, but if you go by 3 to the power 6 k design here, so 3 to the power 6, it is a huge number of runs experiments required, but using Box-Benken this is much less, it is 54 only. So, with this I conclude that in order to estimate the second order regression model or response surface, you require a different kind of design, and that designs which are most popular one are CCD, when it is to the power k level case. To the power k means each factors are 2 levels, and another one is Box-Benken design, when it is 3 to the power k type of case. In the first case, there will be spherical CCD, there is your rotatable one, there is face centered CCD. So, CCD requires 3 kinds of observations, one at factorial points, another set at axial points, and another set at central points, and it has very useful property and heavily used in doing experiments for fitting second order response surface. Box-Benken design employs the concept of 2 to the power k, but it is basically a 3 to the power k design, where two factors at a time consider at the factorial points, and the other factors will keep at the center or level, and all the combinations are used, and that will give you efficient one compared to 3 to the power k full factorial design. Okay. So, next class we will discuss the second order model. Second order model means second order response surface model. So, hope you have understood the CCD fully, and in next class I will use the CCD in experimentation, and the results through CCD whatever we will get, that will be analyzed, and that will be used for fitting the second order response surface. Thank you very much.